Il prossimo intervento è un intervento che io giudico non solo dal titolo, ma è bellissimo, meraviglioso, wonderful. Lo terrà Alok Jha, che è un giornalista, un divulgatore scientifico inglese, corrispondente della BBC, del Guardian, che ha scritto libri importanti, anzi vi ricordo che uscendo dalla sala troverete i libri di tutti i relatori che hanno parlato, quelli che abbiamo chiaramente reperito sul mercato, potete acquistarli, far firmare gli autografi eventualmente, sono tutti libri molto importanti. Ecco, Alok Jha ci dimostrerà come l'acqua è un elemento meraviglioso e uno dei motivi per cui abbiamo organizzato il Labirinto d'acque è anche perché siamo stati incantati da quello che lui riesce a comunicare sulla sostanza dell'acqua. Grazie.
Good morning. Good morning. It's a pleasure to be here today with you all. We are convened here to talk about some really quite important issues around the sustainability of water and the availability of it, and the changes that will happen to our environment in the next few hundred years as environmental pressure builds. And it's really important that we talk about all those things. But in my mind, the reason we talk about any of these things, the reason that any of this is important, is because of the importance of the substance, the material of water. And if I can take you behind the curtain slightly, if I can take you just one step into the physics and the chemistry and the biology of what water is, then it will make, I think, the rest of this meeting for the next few days so much more interesting and important to you. Because there's a reason why we care about water so much, and it's much more than just availability. It's about what it means for us. For me, water is something very, very special, and it is to you too, but you probably don't think about it that way. You think it's there everywhere, it's colorless, it's clear, it doesn't taste of anything, it's kind of a bit boring. But actually this, to me, is the most wonderful and the strangest of chemicals. It's such a strange chemical that because it's created us and it's required for all of our lives, we are essentially invisible. It is invisible to us as an element. It's made us not notice it. So let me take you behind the curtain to show you how strange this substance really is. This story for me begins with an expedition I made to Antarctica many years ago. So this is me with my Antarctic outfit on, the ship behind me. 5 years ago, I went to Antarctica on an expedition with some scientists to understand how they do their work. I'm a science writer. I write about scientists and climate change and environment every single day. But I don't really go along with scientists to do their work, and I wanted to spend a bit of time with some scientists to understand what it is about their work that they find interesting. And I spent a month on board a ship going from New Zealand to Antarctica. And there it was. And what you must know about me, I live in London, I don't really like being cold. I hate being cold. I don't like being outside pretty much. I don't really like uncomfortable environments. I'm a person, I live in cities and I liked being comfortable. So this was very, very strange for me to be going to somewhere so far away, somewhere so uncomfortable. But I went there to try and understand different types of water, to see what you see when you leave civilization. And my expedition was with climate scientists, with wildlife experts, with oceanographers, and each one of them had a different story around water to tell me. When you leave New Zealand, this was our ship, when you leave New Zealand to go to Antarctica, the first thing that happens is that you cross the Southern Ocean. The Southern Ocean is one of the most dangerous and rough seas in the world. If you can look at this picture, can you see the horizon? Can you see this is how the ship rocked from side to side for days and days and days on end. Let me remind you, I don't like being uncomfortable, so this was very difficult for me. The first thing that happens when you leave New Zealand is you get sick. And the oceans make you sick because they're so rough. Around 50 degrees south, 60 degrees south as you get to Antarctica. The Southern Ocean is famously rough. The mariners and sailors of the 19th century would talk about the stories. It would wreck ships. The winds around the ocean are so intense because there's no landmass at those latitudes. And so the winds go round and round and round the earth, and they wreck ships. Fortunately, our ship was very strong, and nowadays that doesn't happen. But still, the effects of that rough sea can be really, really horrible. And not just me, but many experienced voyagers also get sick for the first few days. And it takes about 10 days to sail to East Antarctica, where we had ended up. And if you were to look at the Earth from afar, the fact that there's some rough sea in the bottom, in the southern hemisphere, is no big deal. The Earth is a water planet. You look at it, and 70% of the Earth is covered in water. And if you were an alien from outer space, and you saw our planet, you wouldn't see a land mass and countries. You would see water, and then some parts of the Earth that didn't have water, but probably were less important. The water is the important thing. And we know it's important. Half of the oxygen in the atmosphere comes from organisms inside the oceans. We think that life itself started down at the bottom of the ocean somewhere. The oceans control the world's weather. All of life depends on this water. It's incredibly important. Every culture in the history of humanity, from the very first to now, water is an important part of the rituals, of the sacraments. If you are a reader of the Bible, you'll see in Genesis, the very first lines are how God creates the earth over still waters. He creates the heaven and the earth over the still waters. Water is always there. In Hinduism, in Islam, all these things, water is an important part of the cleansing rituals. The flood myths, there are flood myths across all cultures where water cleanses the earth of sin. Water is important. Our ancestors knew that. I'm a scientist, and so my background is in science and trying to understand water. But I find these mythological ancient stories really quite compelling because they are something about our shared humanity. And what I also like about those stories, about this heavenly, transcendental water, is that, in a sense, it's correct scientifically too. Because all of the water on the earth, all of the water inside you, inside the plants, inside the cups, it all comes from the heavens. It came from space very far, a long time after the earth was created. So to understand that, we have to go right back to the beginning of the universe. How does water get created in the universe, and how does it end up on Earth? Well, 13.7 billion years ago, when the Big Bang occurred, the universe began. For a long time, there was nothing. It was just energy. A few minutes into the age of our universe, this is still a very long time ago, all of the hydrogen in the universe is created. So water is 2 atoms of hydrogen and 1 atom of oxygen. So those hydrogen atoms have been here since the beginning of the universe, every single one inside you. So those hydrogen atoms were there, but for a very long time, the universe was just hydrogen and maybe a little bit of helium, but that's it. Where was the oxygen? The oxygen was created much, much later. As the hydrogen spread out through the universe, it would form clumps of clouds, and those clouds would collapse into stars. And this is how stars are formed, when a cloud of hydrogen comes together, and under gravity, the hydrogen atoms will fuse to start shining, and that's what a star is. It's hydrogen atoms fusing, releasing energy. When the hydrogen at the middle of a star all fuses into helium, and there's none left, it will start to fuse the helium into other things too. And the helium will fuse into carbon, oxygen, nitrogen. Those will end up fusing too into heavier elements. And when it can't do that anymore, the star will explode. And you see something like this. This is a planetary nebula. A nebula is the result of a massive star that can't fuse anymore, and it explodes into a supernova, one of the brightest lights in the universe. Now, this isn't a real color picture. The colors here represent elements in the universe, in the galaxy, different elements, clouds of elements. So when a star explodes, the elements that are created are sprayed out into a huge cloud. And this you can imagine as a very sparse cloud of elements. They are nitrogen, oxygen, carbon, all sorts of things just floating now in space in amongst the hydrogen that's always there. This particular nebula is called Helix. It's 7 light years across, and that's a huge distance. Our solar system is only 10 light minutes across. This is 7 light years across. Another one here, this is called the Rosette Nebula, and it's 50 light years across. These are enormous objects, enormous amounts of material created in the middle of stars. And this is probably one of the most famous nebulae. This is the Eagle Nebula, and it's 4 light years across, relatively small. But these dust clouds were created billions of years ago. This is often called the Pillars of Creation as a nickname. And the reason it's called the Pillars of Creation and other nebulae like this are called that, because in amongst this messy, dirty cloud of elements is how things like our solar system are created. So inside this cloud, there's still lots and lots of hydrogen. So another star will form at some point. You can see nurseries. This is a nursery for stars. A star will be created. Our sun was created in something like this. And around it is lots and lots of carbon and nitrogen and oxygen. And so what happens is that those grains of carbon and nitrogen and other minerals will start to form the beginnings of our planets as they circle around the sun. In amongst it all, you will get tiny grains of carbon, ash essentially, tiny grains, and oxygen and hydrogen atoms will just bump into them over 100, 200,000 years. Tiny grains of carbon will have little oxygen and hydrogen atoms hitting them to create individual molecules of water. And those individual molecules of water will stick to those carbon grains and create little coatings of ice. And those little grains will come together to form stones, and they come together to form rocks, and they come together to form boulders, eventually whole planets made of these materials, containing all this stuff that is normally floating around. Now, at the beginning of the Earth, 4 billion years ago, 4.5 billion years ago, the Earth is hot on the surface. It's boiling hot. There's volcanoes everywhere. And all the water on the surface is driven away. It's dry. But clearly we see oceans all around us. So where's it come from? Well, 4 billion years ago, at a point when the Earth is several hundred million years old, something happens at the edge of the solar system. Now, at the edge of our solar system, even today, there are lots and lots of asteroids, comets, the leftover material from the clouds of dust. It's just all sitting outside, far, far away. And so 4 billion years ago, something disturbs those clouds, and lots of asteroids and comets start coming towards the sun. On their way, many of them hit the Earth. So for 500 million years, this planet is bombarded by asteroids and comets, just continually bombarded. It's a very violent place at that time. And every one of those asteroids and comets brings with it a little bit of water. And over that time, that's how our oceans are made. That's where our oceans come from. They come from the edge of the solar system, and they're made very far away from this planet. Now, as you sail the oceans and you get towards Antarctica, after it's very rough, when you get closer, it starts to calm down, and you see ice. Ice is obviously nothing particularly special as far as we're concerned, but what we're seeing in this picture is the remnants of Antarctic winter. So every year, Antarctica in the winter, so that means around May, June, July, August, it expands. The sea freezes and doubles in size. And then every summer, which is when we went in December 2013, that's the Antarctic summer, the oceans the ice begins to melt. So you see this, and the colors of the ice are incredible. As you get closer to Antarctica, the temperature of the water goes down, and it begins to be able to support icebergs. Now, icebergs we've seen in pictures and on television. You may have seen them yourself. They're incredible objects. This one was 50 meters high from the surface, and probably 200 meters below as well. Enormous, the size of a city, this iceberg. And there's so many of them all around. And interestingly, this is, when you're going to Antarctica, the very first actual piece of Antarctica that you see, because this was created on the surface of Antarctica, on the land, as snow falls over hundreds of thousands of years. It builds up into form glaciers, and these glaciers very slowly creep to the edge of the continent, and then occasionally they'll break off, and then an iceberg is a result of that. It floats off into the ocean to melt. And what's incredible about this is not just how beautiful it is and how wonderful the colors are. It glows from within. It's also that this thing has been around for 100,000 years, maybe longer. This is older than all of human civilization. But we humans were barely able to read and write when this was, or even before then. This is hundreds of thousands of years old. And it will be around probably way after we are all gone and this civilization has gone. But to me, there's something even more incredible about this. The fact that it's 100,000 years old, the fact that it's something like through 200 meters below the surface, that's all wonderful. But the fact that you can see this at all, the fact that you are looking at it and not gasping, is the most wonderful and exciting and bizarre thing. Because what you're looking at here is a solid, water-solid ice floating on its own liquid. Now, if any of you have done chemistry at school, you'll know that when something freezes, it contracts, it gets smaller and more dense. That's the point. That's one of the definitions of something becoming colder. It becomes smaller, and then it sinks and gets heavier. So anything that freezes sinks to the bottom of its liquid. This doesn't make sense. Nothing else does this. Nothing else we know of actually gets bigger when it gets colder. And this is just the beginning of how strange actually water is. The reason it does this is because the way that the water molecule is arranged, when it becomes a crystal, when it becomes solid, it forms in such a way that there's lots and lots of space between the individual molecules. And so that means that at 0 degrees Celsius, the freezing point of water, the solid water is less dense than liquid water, and it floats. I mean, it makes sense scientifically, but it's the only thing that behaves like this. And the weird thing is, of course, that when you're drinking your drinks later, or any time you have ice in your drinks and you see it floating, you'll never see how strange that is because we're so used to seeing it. We're so used to seeing something so strange in that we never question it. Here's another example of something that water does that's a bit strange. This is an insect called the water strider. You must have seen these. They slide across the surface of ponds and lakes. And to this creature, water is essentially it's like a mattress. It can't go through. It just slides across. Now, the reason that happens is because water has a very high surface tension. Every liquid has a surface tension. This is the measure, chemically speaking, of how much the molecules of the water or any liquid like to stick together compared to how they like to stick to other things. In this case, water likes to stick to itself more than it likes to stick to the air above it. So that means that there's a barrier. There's a barrier. You have to have a certain amount of energy to penetrate that barrier. We can do it easily. We're much bigger. But that creature can't. And so for that creature, it's very useful. It can go across ponds and do whatever it needs to do. Now, water happens to have the highest surface tension of any molecule we know. Okay, that's interesting, you think. Why is that important? Well, the thing about water is that if you put water into a small enough tube, a tiny, tiny, very thin tube, it will, because of its surface tension, stick to the sides of the tube and pull its surface up against the force of gravity. It will flow up against the force of gravity. And this is very useful if you want to take blood from your heart to the top of your brain. If you want to move water from the roots to the top of a tree, this is how it can be done. No other liquid can move that way, in that fashion. And it tells you something else, that this is why water is so important for life. Water was created in the ocean, life was created in the oceans, and it's fundamental to how life operates. The reasons that water does all of this, of course, is that the way that water molecule is shaped, if you imagine the oxygen atom here, the hydrogen atoms are like this, like a shallow V. And the hydrogen atoms are ever so slightly positively charged. Not much, a little bit. And the oxygen is a little bit negatively charged, electrically. And in the liquid, that means that the hydrogen atom, the positive charge, is ever so slightly attracted to the oxygen of another molecule. And the oxygen of that one is ever so slightly attracted to the hydrogen of another one, which means that water sticks to itself. It's really quite cohesive. And this electrical network in water allows it to do so many of the things that I'm describing now, which nothing else can do. Because look at it this way. The molecular weight of water is so low, it's such a light molecule, that it should really, at this temperature on the Earth, it should be a gas. Other molecules that are exactly the same weight or similar, they're all gases at this temperature and pressure on the surface of the Earth. But this attraction between the molecules of water allows it to remain liquid for slightly longer. Now, if it wasn't liquid, none of us would be here right now. So we should be very grateful of these tiny electrical forces that create all of these things. I could go on, there's many, many more, but I'll move on to the next bit. Now, when you get to Antarctica, this is the first thing we saw. This is the coast of Antarctica. Over the hill is where the South Pole is. It's many, many hundreds of kilometers. You see the Antarctic plateau. And one thing you'll notice, there's hardly any life there. It looks dead. It's completely barren, because Antarctica is the biggest desert in the world. It's dry, has a lot of water, but all the water is solid. Except wherever there is a little bit of liquid water, even in this harsh environment where the winds are hundreds of miles an hour and the temperatures are 20, 30, 40 degrees below freezing, wherever there's a little bit of liquid water, life survives. Of course, the very first bits of life you see when you turn up at Antarctica are penguins. These are Adelie penguins that greeted us when we got to Antarctica. They live on the coastline where they fish in the water and they get krill. There were some of the most magnificent creatures you'll ever see. The closest we could get is this far. They're very, very clever. They won't let you get any closer than that. They're not afraid of humans at all. Other creatures, the seals. This is the Weddell seal. These are all pictures that my colleagues took on the expedition. And these, they sleep during the day and they fish at night. Absolutely beautiful. These creatures live in this extreme environment, but because there's a bit of liquid water on the edge, they can survive. Now, in Antarctica, it's mostly solid water, but there are lakes underneath the ice caps that have been isolated for hundreds of millions of years, and even there, life survives, even in the most extreme conditions. At the bottom of the oceans, there are vents, hydrothermal vents, where the ocean floor is cracked, and minerals and heat come up. And incredible pressures, incredible temperatures, even there, life survives. In the Atacama Desert in Chile and Bolivia, the driest place on Earth, wherever there's a little bit of water dusting, life blooms instantly. Wherever there is water on this planet, there is life. And there is no life without water. And there are extreme, extreme environments around the Earth where water and life can survive. Why is that interesting? Well, I find that interesting because if you can find extreme versions of life on this planet, imagine what there might be elsewhere. And this is where me, in my background as an astronomer, gets excited. Water is the thing that we look for on other planets if we want to start looking for life. And in fact, the history of all space exploration has essentially been a search for water in different places. We now know there's water on every single body on the solar system, from Mercury all the way to Pluto. And there's lots of liquid water too. So if you look at this picture here, taken by the Cassini space probe a few years ago, Cassini, which was one of the most incredible scientific experiments, and which finished recently. This is the moon Enceladus. This is the moon of Saturn. And we know that Enceladus has a huge, thick layer of ice on top. And we also know that underneath the ice is a huge liquid ocean of water. This is very far from the sun. Huge liquid ocean of water. And you can see these geysers of water firing out from cracks in the ice. These were discovered only in the last 5 or 6 years. And that means that there's liquid ocean underneath. And it's not just here. Europa, a moon of Jupiter, Titan, another moon of Saturn, has liquid oceans. These make it really exciting. These are the sorts of conditions that exist on Earth, and life exists here in those extreme conditions. What does this mean? If you think about this, Enceladus is hot ocean sitting on top of rocks, minerals, which is exactly the same condition that we think life started on Earth 3.5 billion years ago. This is all you need for life to start. And if that wasn't exciting enough, then in the last decade, astronomers have discovered, confirmed, at least 3,000 or 4,000 planets orbiting other stars in our galaxy. The assumption now is there must be trillions of these planets in this galaxy alone, and we don't know how many more in the rest of the universe. These planets exist. The opportunities to have liquid water are huge because we know liquid water can exist very far from sources of heat from the sun. So just think, it means that we know that life started in water in one instance, here on Earth. And now suddenly we've got an opportunity for life to have started in trillions of other places in the solar system, in the galaxy alone. There's no reason why, if life started here and exists in these bizarre, extreme environments on this planet, that it can't exist in other places too. We're just at the beginning of this search, by the way. It's something that in the next 20 or 30 years, we will know whether there are creatures, very simple creatures, elsewhere in the solar system or elsewhere in the galaxy. In fact, I think there are missions already planned by the European Space Agency and also by the NASA to go and try and sample some of the water on the moons of Jupiter to see if something exists there that we had never thought of before. These aren't going to be organisms that have radio telecommunications and are living civilizations, but they might be something like microbes, which would be a remarkable moment in our history. Now, water, as I've told you, I've given you a hint of, is strange. It does all of these things. It creates life. Inside you right now, the chemical structure of water means that proteins are working in the right functions. Proteins, when they're made in your cells, are made as a big, long molecule which doesn't work. And then as soon as you put them in water, it folds up automatically into a three-dimensional shape, which means that you can build your body and send messages around it. Water is the thing that makes all your proteins work, all your DNA work. It's the thing that transports energy between your cells and inside and out. It's so fundamental to our life that we don't think about it. I think that what's interesting from a scientific point of view is that we've only recently started to discover how strange it is. And in fact, most scientists are scared of studying water because it doesn't follow any of the rules that they would normally appreciate of other liquids. And I find it incredible that the more we study water, the more mysterious actually it gets, and the difficulty with which it is to actually get to the heart of what it does and why it does it. And isn't it weird that the thing that we are made from, the thing that has made us, is so mysterious? So if you've got some water in front of you now, which I'm sure you do, in a bottle or a cup or anything, just take it out and look at it. This colorless, flavorless, tasteless, slightly boring material is the reason you're here. It's the reason that all of life is here. It's all of civilization exists because of this strange molecule and its strange, strange behavior. Thank you very much. Did you want a question? Yes, please. There's a microphone coming, yeah.
Yes, thanks. Thanks for a wonderful presentation. Very, very interesting. You didn't touch a lot on the internal chemistries of water and how much of a difference that they make in everything in our everyday lives. And one of the most eye-opening experiences that I had in recent years when I learned that there are now fish biologists who are able to track where certain individual fish have gone by sampling some of the jaw bones and determining the chemistry of the jaw bones can tell them, they can detect the chemistry of the water that the fish swam in. So for instance, migratory fish can traverse long distances and they can tell which waters they've been in by this chemistry. Are there other stories about chemistry that come to mind for you that you think are similarly extraordinary in that way?
Oh gosh, yes. I mean, I didn't touch on much of the chemistry because we only had half an hour. I mean, you could do days of talks on the chemistry of water. It really is bizarre in that, when you think of chemistry and science, and all it's about classification, it's about prediction, it's about saying these things behave in this way, and this class of things can be predictable. With water, nothing makes sense. Nothing at all makes sense. So, yes, water on this earth, for example, we still don't really know where it came from, but it has a particular signature. So, water exists as H2O, hydrogen and oxygen, which is most water. But hydrogen can come in many forms. There's heavy hydrogen, deuterium, and so just naturally occurring, some proportion of the water is made of deuterium and oxygen, which is heavy water. We know it relatively well. We use it for our purposes in car batteries. And another version is called tritium, which is radioactive, and we need that for fusion energy if one day we're going to use that. So these waters exist, and every sample of water on the Earth contains a particular proportion of hydrogen and deuterium. So then you know exactly where it's come from. Scientists can measure this. But also, it's the key to understanding where the Earth's water came from. We're still looking right now at where in the solar system those asteroids came from. They're somewhere in the solar system. And do you remember 3 or 4 years ago, the wonderful space mission, the European space mission, called Rosetta, which looked at landing a spacecraft on a comet 3 years ago. It was an amazing expedition. Many, many Italian scientists involved. In fact, they ran the expedition. And we landed on this comet to take a sample because we thought that this is coming from the part of the solar system where our water came from. Turns out it didn't. So then we've now crossed out that little bit. Now the rest of the sky is still open for search. Somewhere is where our water came from. You can track the water in the entire universe like this, and it's our unique one. I mean, that's one story. I've got many, many more if you want to talk about them later.